Hello class. Hello class. This is Ms. Riggins with today's video on section 2.5, the second derivative. Please remember as you're watching the video to take down notes, writing down important formulas, statements, equations, or patterns, as well as any questions you may have. At the end of watching the video, don't forget to write down your video summary and submit that via the online whisk form. Feel free to pause, review, rewind, or watch the video multiple times to get a full understanding of what is being said. And now let's begin. We've been dealing with the derivative of a function for about a week now, and we're going to look at the second derivative of a function. Why can we look at the second derivative of a function? Well, if you remember last week, we talked about that the derivative is a function. The derivative relationship is a function. So if the derivative relationship is a function, then we can take the derivative of that function, and that derivative is called the second derivative. There are multiple ways to represent the second derivative. One way is by calling it f double prime. Another way is by calling it the derivative of dy dx, or in notation, the derivative of dy dx. Or you may see it as d squared y over dx to the squared. Why is it d squared y? Because as you can see, we're squaring the dy, the dx. Okay, so let's talk about what the first derivative tells us, and that may lead us to give us information about what the second derivative will tell us. The first derivative tells us about the function besides the slope of the tangent lines at each of those points. It tells us if the function is increasing. If the derivative is positive on a particular interval, then that would mean that the function f is increasing over that interval. And this is review. And if the derivative is negative on that interval, then that means that the function is decreasing over that interval. Well, using the same sense of using that same reasoning, we can apply this to the second derivative, because it's just like the first derivative tells us about the function. The second derivative tells us about the first derivative function. So if f prime is increasing over an interval, i.e. the first derivative is increasing over the interval, that means the second derivative must be positive on that interval. And if the second derivative is negative on an interval, then that means that the first derivative must be decreasing over that interval. Okay, well, what does it mean if a function's derivative is increasing over an interval? We know what it means for a function to be increasing over the interval, but what does it mean for a function's derivative to be increasing over the interval? Well, what that means is something you may recall us talking about in pre-calculus. So let's take a look at two types of functions and see what the second derivative can tell us about that. So here I have two different functions, and as you can see, the function f over here is graphed like this, and the function f on this case is graphed like this. And as you can see here, the function is decreasing, so that means the first derivative would be negative on this interval. And it gets to this point, and then the function starts increasing, which would mean the first derivative would be positive on this level. Well, when a function goes from decreasing to increasing, that means our first derivative, as we know, goes from negative, from less than 0 to greater than. But since the derivative is going from negative to positive, then that must mean that the derivative is increasing on this interval. And if the derivative is increasing on this interval, then that means that the second derivative is going to be positive over that interval. What does it mean if the second derivative is positive? Well, it looks like we have something that looks like a concavity issue. It seems like the graph is going concave up. And that occurs when the second derivative is positive. If we take a look over here, in this case, the function is increasing on the interval, and then it starts to decrease. But if we take a look at its derivative, how the derivative is changing, we see that the derivative is decreasing because it was positive, then it goes to 0, then it goes to negative. So if the derivative is decreasing, the first derivative is decreasing over that interval, then what does that say about the concavity of this over this interval? And it seems like the concavity is concave down, which would mean that the second derivative is negative. So as we take a look at that, we can summarize that in this statement. If the graph of f is concave up, and f the second derivative exists on that interval, then the second derivative would have to be greater than or equal to 0 there. If the graph is concave down and the second derivative exists on an interval, then the second derivative is less than or equal to 0 there. Now, I know some of you are saying, why is that greater than or equal to or less than or equal to when over here we didn't see where the second derivative was equal to 0? Well, that's because that the second derivative being equal to 0 means that the rate of change of the first derivative is 0, which means that it's neither concave up nor concave down. But we can say that the second derivative is positive, including 0, then that means the graph is concave up. If we can say the second derivative is negative, including 0, we can say that the graph is concave down. Because when the second derivative is 0, it's one of those funny situations, which we're going to look at a little bit later in class. So how does that work in terms of position and speed? Well, we talked about earlier in class this concept of acceleration, and the physics students knows what that means. Or if you experience physics with velocity and speed and acceleration, you know what it means. But mathematically, let's take a look at what that means. The average acceleration is the rate of change of velocity over a particular interval from t to t plus h. So if I want to look and see what the definition of acceleration is instantaneously instead of average, it's basically the first derivative of the velocity function, which is the limit as that h approaches 0 of the velocity of the difference quotient of the velocity between two input values divided by the difference of the input values. So in other words, velocity, the first derivative of velocity is acceleration, or acceleration is the second derivative of the position function. So let's take a look and see how that represents. So let y equals s of t be the position of an object at time t. So that means we have some type of position. So that would mean that the velocity is a function v of t, which can be expressed as the derivative of the position function, i.e. s prime or dy dt. And in this case, we're dealing with time. And the acceleration function is the first derivative of the velocity function, which is the second derivative of the position function, which can be represented as the second derivative of y, or d squared y over dt squared. And we're going to look at problems where we use all of those three together. Now, some of you have been asking about how to use the second derivative in a problem or a question. Well, you haven't been asking that, but I know you guys are going to ask that. So let's take a look at a problem. And we're going to graph the second derivative of the graph function just from the original function. So I took this from number 23 from your textbook exercises. And here is a graph of an original function, well, the original initial function f. And I want to graph the second derivative of that function. Now, here's the tricky part. One way alternative is to graph the first derivative of this function and then graph the derivative of that function. And we could do that, but that's a little bit more tedious. In calculus and in math, we're trying to teach you how to work more efficiently. So the idea is, can we skip graphing the first derivative and just graph the second derivative from the original function? And we can, using the fact about the relationship between concavity and the second derivative. So where is this graph concave up and where is this graph concave down? Well, as we can see here, the graph is concave down here, from here to here. And then it's concave down again from here to here. So if the graph is concave down in these situations, then I know that when I graph the second derivative is going to be, well, if you remember from our notes, that would mean the graph is negative of the second derivative. And so therefore we can draw negative, and it turns to, so it's negative up into, it's negative up into, let's say this point right here. And then it changes and becomes concave up, which will mean positive for the second derivative. But then over here, it becomes concave down again. So I can draw this here on this interval from here to here. So it must mean that when it's concave up, in this situation right here, the second derivative is positive and it goes up like something like this. Okay? All right, that ends the introduction part as well as an example. I really encourage you to get a good understanding of what it means to be a second derivative, conceptually as well as, of course, numerically. It's easy to calculate the second derivative if you have the first derivative, because you're basically doing the derivative of that, which you have practice with. All right, see you in class.